Welcome to Lecture 19 of Statistical Rethinking 2022. In this lecture, I want to get back to the scientific foundations of statistical modeling and show you another path than the common one that we've taken so far. It's a real benign aspect of the universe that linear models work at all. Linear regressions and the generalized versions of them, generalized linear models and generalized linear mixed models, have at their heart additive combinations of variables. They're the square hole of nature. And as the square hole of nature, we can use them for things that aren't square, because the square accepts all. But this is a bit disappointing from a scientific perspective, from a research perspective, because when we put the round peg in the square hole, we're giving up some scientific power. The fit is okay, but it's not ideal. We give up some statistical power on one side because the statistical model is ignoring some important features. But we also give up some opportunities to use scientific information to better inform the statistical analysis and get more that way as well. Generalized linear models are probably more than 90% of all the modeling done in the sciences, and much of it in industry as well. And that's because they're really useful. They're incredibly flexible association machines, epicycle devices that can construct useful approximations of the associations between many sets of variables. And as I've argued at length in this course, as long as you've got an external causal model that you place some minimal credence in, then we can interpret the coefficients of GLMs and GLMMs causally, which is usually what we like to do in most scientific and industry analyses. No matter how big the GLM, it's still just a GLM, right? Just as tigers behave like house cats, they're just bigger. GLMMs are capable of lots of really cool things and partial pooling. I hope I've convinced you, but they're still just linear models at their heart. So we should deploy them with caution. They're the square hole with which we could stuff all of our scientific phenomena, but that would be giving up some additional power. There are two big problems with using GLMs all the time. The first is there are lots of scientific phenomena that really can't be usefully expressed as GLMs. And so if all you've ever been taught are GLMs, then you really can't even get started on these problems. The second is that even when we can use GLMs or their bigger cousins, the GLMMs, the tigers, if we start from a more scientific causal perspective and build up towards a joint causal and statistical model, we get to use more of our scientific knowledge, and it helps us solve actual empirical problems in the analysis. So in the lecture today, I want to show you a few examples of these things, the simplest examples I could think of, to prime your imagination and give you a glimpse of other kinds of techniques for jointly, simultaneously doing the causal modeling and the statistical modeling. Let's start by revisiting one of the very first data analysis problems in this course. Early on in the course, I used the example of the causal influence of height on weight for humans as a way to motivate lessons in building linear regressions. We're going to come back to those same data now, the Howell data set from early in the course, and build it up a completely different way. So to build it up a different way, I want you to consider this idealized, at least from the perspective of a certain Italian, human on the slide. If we make this human taller or shorter, they get proportionally lighter on the left or heavier on the right as a consequence of that scaling. And that's because other things scale with height. most particularly the volume of the person's body, and weight is a consequence of volume. That's where we get our mass. So using those geometric principles, we can build up to a scientific model. Of course, there are subtleties here, and I'm going to beg your indulgence to ignore those subtleties on the first pass. In particular, for example, it's true in humans that children are a bit wider for any given height than adults are, and very tall adults tend to be proportionally thinner than shorter adults. And so there are other kinds of things that change with height as well in terms of the geometry of human bodies. But let's just take a first pass ignoring those details and see how far we can get. And I hope to convince you get pretty far just by using the basic geometry. So let's think about a geometric person. In particular, suppose people are cylinders. I know, we're not cylinders, but let's start here and see how far we can get. And by saying that people are cylinders, what I mean is where our main length dimension is our height, and we then have some radius from outward the center of our body, and we can compute the volume of a person as an approximation using the equation for a cylinder. And what is the volume of a cylinder? Well, you learned sometime in secondary school and then forgot because it was useless to you that the volume of a cylinder, V on this slide, is equal to pi r squared h, where pi is pi. R is the radius of the cylinder, shown on the diagram on the right, and height is the length of the cylinder, the height of the person. Okay, so now we're going to approximate the person's volume using their height. This is, in a sense, the causal influence of height on volume. Causal because it allows us to do interventions and predict the consequences of those interventions. That is, this equation tells you if you change a person's height, how their volume changes. The thing about the human cylinder, as it were, is that there's a certain proportionality of the width of our bodies, that is the radius of the cylinder, to our height. We don't usually think of ourselves as having a radius, but we can think of ourselves as having a body width, a shoulder span, that is some proportion of our height. And so we can replace the radius with that. This product pH, or P is some proportion, and H is just the height again, and this replaces the radius. And then finally, our weight is some function of our volume. And so I'm going to introduce this parameter K, which you can think of as our density, that is, how much weight is generated by each unit volume of a person. Okay, so now we have an equation for a person's expected weight on the left here, and that's data. We've observed that as a function of some density parameter K times pi times a proportionality parameter P that is squared times their height cubed. It's a volume after all, and this is also data in our case. Now we need to use this to build a statistical model. As you know, because you're pros at this by now, we're 19 lectures in after all, in order to take some equation for an expectation and make it into a statistical model, we have to consider a bunch of plausible observations implied by that expectation. And this usually means, as it does in this case, choosing some kind of error distribution for the observable variable. And so observed weights, we don't expect them to exactly lie on the line described by the equation here for mu, which is the expected weight. We expect them to have some distribution around it. So that's the first thing we have to do, as shown on the top of the slide, is pick some probability distribution for the observable, and then its expectation comes from our geometric person model, the cylindrical person model on the second line. And then since we have two parameters, we need priors for them, or otherwise to fix them from the background literature. That'd be another option as well. So let's think about how we set these priors. And I want to actually go through three different features that apply to many examples, but apply in really interesting ways, I think, to this example. And the first thing we can do when trying to decide upon priors is it often pays to think about measurement scales, and sometimes even to change those measurement scales. And that's the first thing we'll examine. The second thing, as I've shown you in many examples in this course, is it's useful, in fact, typically required for understanding priors, to simulate from them. Simulate the implied observations of the models having drawn parameter values from the prior distributions. And we'll do that as well. And then finally, we're going to think, which is always a good idea. So let's start with choosing measurement scales. What do I mean by that? Well, in statistical models, even though we don't usually write the measurement units, the units of the scales on each variable, variables often have units. So in this particular case, for example, mu sub I is an expected weight, and it's in kilograms in our raw data. The observed variable on the right-hand side of this equation, height, is in centimeters, and so height cubed is in cubic centimeters. Those are its units. And this means that the units of the parameters are determined by the units of the data. I'll say that again. The units of the parameters, what they have to be, are determined by the units of the data, in the sense that in order for mu sub I to have units kilogram, the parameters have to have the right units to effectively cancel the cubic centimeters of h cubed. And the only parameter we've got that can have units here is k. P can't have units because it's a proportion, and proportions are unitless. But K must have units, kilograms per cubic centimeter. It's a density, and that means that when we multiply K times H cubed, the only units that don't cancel are the kilograms, and it all works. The units balance. Some of you will remember exercises like this back in secondary school sciences, right? Maybe you haven't done them in a while, which is fine. This stuff is always lurking in statistical models as well. And it on the first pass, one of the things it lets us do is it gives us a way to look up relevant information about the parameters. So for example, with K here, what we need to know is how many kilograms are there per cubic centimeter of person. Now, I don't know. I wouldn't Google that. I'm not sure what I'd get. But you might try to look it up, or at least it gives you constraints in some ballpark way to think about a prior. I want to do something else, though, here. That it's often much more useful. And that is, we want to get rid of these units altogether. And the reason is because measurement scales are a human artifice. Now, artifice is not a terrible thing. All technology is artifice. It's artificial stuff we've come up with. But sometimes, when you're trying to construct one artifice, the existence of another artifice is a problem. So we can get rid of the artifice of measurement scales. It turns out this problem becomes easier. So how do we do that? Well, just take your observed variables, like weight and height, and divide them by some reference value. So and that could be anything that you think is scientifically useful. And when we do that, it'll cancel the units. So for example, you look on the right of the slide, I have the raw data plotted, height in centimeters against weight in kilograms. And for each of these variables, there's a mean in the sample, the mean height and the mean weight, and I've indicated them there with those dashed lines. If we divide all the weights by the mean weight and all the heights by the mean height, we construct new observed variables, which are all proportions of the mean. And it doesn't change the relationships between the people in this, but it removes the units. And now these are unitless or dimensionless quantities. They're natural quantities now, where we measure weight in terms of a proportion of the mean weight and height in terms of proportion of mean height. There's nothing special about the mean here. As I said, you could choose anything you like. You could choose average adult weights and heights instead of just a total average, anything you like. But the point is that this exercise here removes the units. And now we think about these dimensionless parameters that are still relevant to that focal point of the combination of the mean weight and the mean height, which is an interesting focal point because we know from definitions of mean that at the mean height, individuals will tend to be of the mean weight. I'll say that again. At the mean height, we know that individuals tend to be of the mean weight. And so the trend line, the statistical description we're looking for should pass close through the points 1 and 1. That is a height of 1 and a weight of 1. We can think about these parameters now and simulate from them with this background knowledge in mind. P needs to be some distribution. And it's a proportion, so it has to be bounded between 0 and 1. And for humans, at least, it's going to be less than a half. And the reason is because there aren't very many people who are as wide as they are tall. In fact, there are essentially no people who are even half as wide as they are tall, unless you're a baby. And then for K, the density parameter, now dimensionless. It's just like a proportion of volume that determines weight. This is a positive number. It's a proportion, but it can be greater than 1. And in fact, in this example, it's going to have to be greater than 1 in order to produce equations that make any sense, descriptions of the association between height and weight that make any sense at all. I'm going to propose these two distributional choices, and then we're going to simulate from them, because these have the basic properties we want, and they'll push the lesson forward so I can reveal some other things about this business. So for P, we choose a beta distribution. A beta distribution is a probability distribution for probabilities. So it's got the right bounds between 0 and 1. And the parameters here, 25 and 50, are chosen so that all the probability mass, almost all of it, lies below a half. But it's also not near 0, right? And you can see what this distribution looks like on the right there. And then for K, an exponential with a rate of 0.5 that gives it an expected value of 2. So the expected value here is greater than 1, and it's constrained to be positive. Let's see what these look like. What kind of growth equations, equations predicting the causal influence of height on weight, do we get from simulating from these priors? You've done prior predictive simulations a lot in this course, so I don't think I have to explain all the details of the code on the left again, just to say that it produces the curves on the right. Those are 30 different draws from independent priors for P and K, and then we simply draw the cylindrical human model. The range of possible functions generated from these priors is really huge. In fact, it's almost certainly too large to make scientific sense, but you can see what's going on the right there is we get many functions relating height to weight which are implausibly too low or shallow, pressed up against the horizontal axis. It's as if people are filled with helium, and then ones that rise much too fast, as if people were made of steel. And I still have the reference point between a height of 1. Remember, this is scaled. That's 1 here means the average height, and weight of 1, which means the average weight. And the relationship, the real relationship between these variables needs to pass near that point, 1, 1. It's the only thing that makes any biological sense. And that gives us a sense about how scattered and strange these priors are. But let's press forward, because I think you can see that with a few more steps as we push into this. The only thing left to get a functioning statistical model is to choose the error distribution. And in this business of choosing distributions, as I keep saying, you want to think about the constraints on the variable that you're assigning a distribution to, and think about what scientific information you have about it as well in terms of its scaling. So in this case, what's relevant is that weight is a positive real number. It's bounded at 0, has to be positive, and its variance scales with the mean. That is, the error we expect around a certain weight as a function of height gets larger. That is, heavier Taller people occupy a wider range of weights than do shorter people. And that's a consequence of the biology, because there's potential for much more variation in weight for individuals who are tall. And so there are lots of distributions you could choose here, but a very convenient and scientifically justifiable one is the log normal. Log normal is justifiable because it's a basic distribution arising from growth processes. I mentioned this early on in the course and also in the book. Growth is a multiplicative process, not an additive process. How much stuff you already have determines how fast it can grow proportionally. And so a log normal is a very natural choice here. The thing about the log normal that's a bit weird, though, is it's traditionally parameterized in a frustrating way. And I'm not going to break with tradition, because that would be even more frustrating. Instead, I'm just going to note to you the frustration of the tradition here. The log normal is parameterized with two parameters, mu and sigma, but the mu here, as well as the sigma, are not describing directly the shape of the log normal, that is, the distribution of the observable variables w. They describe the mean and standard deviation of the logged distribution, of the normal distribution that you get by logging the values w. And this is an unfortunate historical fact. The mean of a log normal is a function of both mu and sigma. And you can look up the equation for that if you like. So when we keep in mind then, if you want the expected value of Wi to be governed by this cylinder model that we've developed, you need to exponentiate it, right? So that it's not, otherwise it would be the expected value of the logarithm, and that's not what we want. I know it's annoying, but this is the way all software works, and the way all of the literature on statistics works is that log normals are parameterized by their latent normal distributions. Okay, but that's okay. We can just put a little exponent link function in here in the model, which implies that mu is the log of that equation, and we're off. We can write this in an Ulam model as normal. Yeah, and you'll see how I've done it here. I've actually written out some of the digits of pi. You could also use the symbol pi, and you can run these chains, and they sample unproblematically. And we get a curve. I show you here is so the red points are the sample scaled, so that one means average height, and one on the weight scale means average weight. And we draw the expected relationship from the posterior distributions of P and K here on this. And you can see it does pretty well. It finds the nonlinear shape no problem, but it's not doing a great job for kids. You'll see it predicts that they should be lighter than they are. And you probably have some ideas about why. This is not bad for a cylinder, I think you'll agree. Very little has gone into this model, just the equation for a cylinder. But people are approximately cylindrical. We're governed by the laws of geometry. So we get a lot, very far along in our modeling task just from this. But there's a very poor fit for children. And the nice thing about this is that well, it's not nice to have a poor fit, but the nice thing about a poor fit when you have a scientifically motivated model like this one, the one that starts from the basic geometric principles of a body, is that how the fit is poor gives you information you can use to put more scientific information into the model. I'll say that again. When you get some misfit in a scientifically motivated model, that misfit is informative of what the model's missing. And it leads more immediately, to ways to alter it and make it better. So, for example, in this case, we're under-predicting the weights of children. This is almost certainly because the P parameter, that is the proportionality, is different for kids. Kids have shorter legs and arms for a given height relative to adults. That is, the proportional contribution of their legs to their height is smaller. So they're wider. There's more of their total mass is in their torso, and especially their head for very young kids. We know things about that though, and so we could adjust this so p is different at different ages and possibly do better. But that's a biological insight, not a purely statistical one. If we had a purely curve fitting exercise here, like a quadratic or a spline, it wouldn't be possible to read out information like that. So we can actually get scientific insights from the misfit of our model. And I think that's pretty cool. Okay, I said we were going to do part 3, which is thinking, and that's a bit mysterious. What do I mean by that? Let's look at the cylinder model a little bit more deeply and think about what it implies about the values of k and p. So I put the equation for the mean here, the mean weight that we derived from the cylinder model, and I want you to consider the posterior distribution of k and p squared from the model we just fit a couple slides back, and I've put it up on the slide here. This is a very weird posterior distribution. The joint distribution of k and p squared makes this strange curve, a bow in the parameter space. What is going on here? When you see something like this from a model, it means that there's some combination of these two parameters that you're identifying in the posterior, but it's not possible to say what the individual values of k and p are. I'll say that again. When you see something like this in a posterior distribution, that there are two or more parameters that form some ridge like this, it can be bent, it could be straight, that means that what you're identifying is not each individual parameter, k and p squared in this case, but you're identifying their product, some function of them. And you can probably get a hunch why by looking at the equation a little bit more closely. You'll see that k and p squared are multiplied together in this equation. And that means, since there are many combinations of k and p that will produce the same product, we can't, with only data on weight and height, identify k and p individually. We can only identify their product. And that's what exactly has happened here on the right. And this is no problem. The model still works. Bayes does what you asked it to do. But this gives us a hint about what we can do going forward. And in particular, I want you to note as well that there's this magic inflection point that was defined by removing the units, making weight and height dimensionless by dividing them by their mean values, is that the function that describes the association, the mean association between height and weight, should pass through or very close to the points 1, 1. So I do this on the slide now. We put in 1 for the expected weight and 1 for height. And this is something that should be approximately satisfied in any good solution to this statistical problem. And this if you solve this equation for k, you'll see that it implies that k is equal to 1 over pi p squared. Let's plot this function, k equals 1 over pi p squared, over the posterior distribution, and you'll see that's exactly what the model has found. It shifted a little bit down because of the exact values and the error distribution. But this is what's happened. It's a consequence of the cylinder again. That simple assumption that people are cylinders has generated a lot of hidden structure in this problem that we could understand purely without data. We could anticipate this relationship before we even fit the model to data. And furthermore, let's push this a bit further. So we know that k and p squared can't be identified. There's just this function that they trade off against one another for fit. We could replace them with just one symbol, theta, which is their product. So I do that on this slide here in the middle. And that means in order for the equation to be satisfied, 1 equals pi theta times 1 cubed. Remember, 1 cubed is 1. It's a nice thing about the number 1. That means that theta has to approximately be 1 over pi, or pi to the minus 1. Otherwise, that equation can't be satisfied. And so do we need any parameters at all in this model? No, we don't. Except for the error parameter sigma on top, we don't need any free parameters inside the equation, and that's a consequence of removing the dimensions from the variables weight and height. Let me show you. Here's a model for this that has no parameters inside the expected value for mu. It's a dimensionless model where weight is equal to h cubed. The expected weight is equal to h cubed, but then there's this log normal variation around it from sigma that we still estimate. And we fit this and we get almost exactly the same relationship that we'd estimated before with two free parameters. Here again for comparison. This is the kind of thing we get from thinking carefully about how we've constructed our measurement scales, or in this case removing them, and what parameters mean, and the constraints defined by the basic scientific model itself, which points it must pass through. Let me sum up. So in this particular example, most of the relationship between height and weight is just the relationship between length and volume, which is not something that's up for debate. Right? The relationship between length and volume depends upon the shape of the container, and when we take those principles and put them together into an approximation of human weight, we get really far, very close to a satisfying answer with very little effort. In fact, we don't even need to fit the model to data, is what I've showed you. Now, of course, there are parts of the height distribution here where the model fits poorly, but that's good in this case because it's a scientific model, and those local problems give us insight into the biological processes and how they vary across individuals of different height, or effectively in this case, how the shape of the container changes over the life course of people. So this is an insight we get, and you only get this from scientific models, or maybe I shouldn't say only. It's much more difficult to get insights like this from purely statistical models, because purely statistical models are epicycles. They're just trying to approximate things, and the parameters don't have any real-world biological meaning. The way people like me think about these things is that there's no effective empiricism without theory. And I hope this little simple example, it's a toy example, but I hope it's convinced you of that that's a plausible position to take, that a little bit of thinking about the scientific phenomenon itself from a causal perspective, plus the universal constraints on the measurements we have, get you really far along to empirical solutions. And a purely empirical attempt to just fit curves to things is going to work out much less well. Okay, let's take a break. Please take a look through the previous slides, make notes of any things that were confusing, and when you come back from your break, I'll pick up with some other examples. Welcome back. With the next example of moving beyond generalized linear madness, I want to talk about child development, and in particular, the ways that children use the behaviors of those around them to learn about their world. So, there's this experiment from the study of child development, cross-cultural child development, that uses this little device on the screen. This is a device that receives tokens or little balls in the pipes at the top and dispenses toys, which children like. And the way the experiment works is put yourselves in the shoes of the child who's participating in the experiment, and the first thing that happens is you watch other children interact with this device. The first child comes along, puts a token or a little ball in the red tube and gets a toy. Then another child comes along and also puts a token in the red tube and also gets a toy. And then a third child as well in the red tube. The fourth child comes along and puts the token in the yellow tube, gets a toy, and then again in the yellow tube, and a third time in the yellow tube and gets a toy. Now it's your turn. You're given a token and you can put it in any of the tubes, either the red one or the yellow one or the blue one. What will you choose? In this experiment, of course, it's run by psychologists, so everything's counterbalanced. The three different children who all choose the same option are known as the majority choice. A majority of kids choose red in this example, but it's not always red. It could be any color. And the girl at the bottom in the green shirt who chose the yellow option by herself 3 times, sometimes she goes first, so that the order of whether the minority choice, that is the girl in the green shirt, goes first, or the majority choice, the other 3 girls, goes first, is counterbalanced across participants in the experiment, and the colors are varied so that it isn't always the same color. That is the majority choice or the minority choice. What kind of data do we get out of this experiment? Well, there are 3 possible outcomes. The child who does the choosing after seeing these 4 girls make their choices can choose either the majority choice, which is in this example red, or the minority choice, which is in this example yellow, or the unchosen option, which is in this example blue. But remember, the colors are counterbalanced across trials. So why should we care about this? Well, there's a big scientific literature interested in the social learning tendencies of kids, and in particular, the ways in which kids use heuristic forms of social learning to more quickly learn about the norms and successful behaviors around them. And part of this is the idea that copying the majority is a very good heuristic in many circumstances, but certainly not all. And so we're interested in having some way to study the development of that heuristic, if it exists, in kids as they age. Do children copy the majority? And if so, how does this develop over time? The problem in this experiment, and in all experiments that study social learning, is that we can't see the strategy that the children are using, only their choices. And there are many different strategies that will produce the same choice, but at different rates. Another way to say this is that the majority choice, that is, whichever color was demonstrated by the majority, is consistent with many different strategies. So think of it this way. Consider 3 different random strategies for choosing which color to put your token into. You might choose a random color, in which case you would, by chance, choose the majority option 1/3 of the time, because there are 3 colors, and one of them was the majority option. Or you could copy a random demonstrator. That is, there are 4 kids, and 3 of them have chosen the majority option. And so if you copy another child at random, 3/4 of the time you'll choose the majority option, which looks a lot like majority preference. Or if you choose a random demonstration, that is a random instance in which a child put a token in a tube, you'll choose the majority option only half the time, because the little girl in the green shirt there made 3 choices, and each time she put her token in the yellow tube. Each of these is different strategy, and I'm not arguing for any particular one. I'm just trying to make the point that the behavior we observe when we study learning strategies is not the strategy itself. And so when we study these phenomena and analyze data from experiments on learning, we need something other than the basic generalized linear strategy before, because those strategies only model patterns in outcomes, in observables. And what we're trying to make an inference about here is something that cannot be observed ever, and that is the strategy or what has been learned. We can only observe the emissions of what has been learned, but we want to infer what has been learned. There's a big literature that addresses this, but before we get to a solution, it might be good to prime your intuition by doing a simulation. So here's a very simple simulation, the simplest one I could think of, to illustrate the problem. Suppose we have 100 children, and half of them are just going to choose a random color. That's their strategy. We simulate that on the Y1 line. Each of them is just samples, an option from 1 to 3 in this. Remember, there are three outcomes: majority, minority, or unchosen, and half the kids do that. The other half follow the majority, which means they always choose option 2, which is just what we're coding the majority option as here. Well, when we observe a sample from such an experiment, all of these are mixed together, and we don't know the strategies of the kids. We only know their choices. And so when we plot their choices, as I've done on the right, the majority choice is a mixture of the random choosers, as I'm calling them, and the majority followers, as I'm calling them. But you don't know which is which. How can we approach this problem statistically? You probably guess what I'm going to say. I'm going to say we need a generative model. And that's right. We need to back up and think about what we're doing scientifically, not follow generalized linear madness, build up from some process model of the system, and see what it turns out to be. So in this case, we're going to end up with something that's known as a state-based model. State-based models are models where there's some hidden state of each agent in the system, and that's usually not observable, or at least it's not observed, but we do get to observe some aspects of the behavior of the agents in the system, in this case the children, and that behavior gives us clues, probabilistic clues about the states of the children. What does state mean here? In this particular case, the state of each child is the child's unobserved strategy, the heuristics they've used to make choices. And just for the sake of the example, I'm going to consider a strategy space that consists of 5 possible strategies, and these are listed at the bottom here. Majority, meaning that the child copies the majority choice, the one that the 3 different children demonstrate. 2 is the minority choice, the one that the one girl who chooses 3 times chooses. 3rd is maverick. This would be a child who chooses the unchosen option every time because no other child chose it, and they really want to see what comes out of that one. The 4th would be a random color. Just ignore all the other kids and choose your favorite color, for example. And then 5 is follow first. And this means copy whichever color was chosen first by the first child that demonstrated. And the way we build this into a statistical model is, of course, to think about it generatively, but run it in reverse. So we have this observation y sub I, which is the choice of each child, of each ith child. And this is coded so that there are 3 options. Number 1 is the unchosen option, the one that none of the demonstrators chose. Number 2 is the majority color. And number 3 is the minority color. And this is going to be a categorical distribution. It's just an extension of a Bernoulli to 3 options. And the parameter that describes the shape of a categorical distribution is just a vector of probabilities, one probability for each option. And that's theta on the screen here. So this is going to be the focus of our attention in modeling, is we need to think how different strategies produce this vector of probabilities. So let's dig into it. So this expression on the screen is going to look like a mess if you just glance at it, but let's just work on it slowly from left to right. So on the far left, we have theta sub j, which is just one element of the vector theta. It's the probability of any particular choice j, where j is 1, 2, or 3. So what we need to do to define the probability that a child chooses any particular option is average over our uncertainty about which strategy they have, because of course we don't know. We can't observe it. And so the next thing that happens is we average probabilistically over the strategies from 1 to 5. And that's what this big sigma is doing here. It's just a sum over the different strategies. And then inside of this sum, we're going to have weighted terms for each strategy, weighted by the plausibility of each of the different strategies. So the next thing, for any particular strategy S, there's some prior probability of that strategy S. And we're going to update this using the data and have a posterior distribution for each. And then each strategy S specifies exactly the probability of a child choosing any particular option, assuming the child is using strategy S. So for example, if a child is following the majority, then they will always choose the majority choice. And so if we observe the majority choice, if y sub I equals 2, which just means majority choice here, then this probability is 1. But if y sub I is 1, unchosen, and the child is following the majority, then this probability is 0. The other strategies imply different probabilities, but they all have this kind of logic. And finally, we need a prior for the vector of probabilities for each strategy. And we're going to use this Dirichlet probability distribution again. This has come up before in the course. I won't review it now, just to say that this is a probability distribution for probability distributions. So we can draw simplexes, that is, vectors that sum to 1 from the Dirichlet distribution for our vector p. Okay, I'm going to do this model in raw stand code. And the reason is because it would be extremely awkward and difficult to do it in Ulam. That's typically true. Ulam is a tool that was meant to help you learn generalized linear models and generalized linear mixed models, and you can force it into service of things much more general than that. But once you go beyond generalized linear mixed models, it's usually much more convenient to work directly in some probabilistic programming language like Stan or Turing or PyMC. Okay, so this is our Stan model, and I just want to highlight a few things about it to help you understand it if you're not familiar with Stan code. In Stan code, we have to declare every variable, that is every observed variable here in the data block up top, and every parameter. So first, this y vector is an integer vector, which are the observed outcomes, and it can take the value 1, 2, or 3. This is the thing that the model is predicting, as it were, that we have to supply likelihoods for. The only parameter we're estimating is a simplex of length 5. A simplex is a vector that sums to 1, and this is the p vector, where there's one probability for each strategy, and we're going to update this using the experimental data so that we end up with a sort of proportion for some population of kids who have used each strategy. All the action is in the model block, and this is where we specify how the strategies translate into probabilities of observations. The first thing is there's this vector I declare at the top to do the work, theta sub j, and that's this is going to hold the terms of this sum that you see on the right. That's why it's of length 5, because there are 5 strategies. Obviously, we declare the prior. There's no surprises there. And then the main action is in all this if-then logic as we loop over each of the children in this big for loop from I to from 1 to n, because they're in observations. And what happens here in each of these if statements is the logic of each strategy is expressed. And this is something you have to do when you do the coding. So let's think about the majority one first. If yi equals 2, which is the majority choice, then theta j1 equals 1. Why is it theta j1? Because 1 is the index for the majority strategy. So this is saying that the probability of observing, the probability that a majority following child would choose option 2 is equal to 1. And then the next one for the majority, the probability that a minority strategy child would choose option 3 is 1, and it's 0 otherwise. And we've filled the theta j vector with zeros to start at the top there. And the maverick, similarly, the probability a maverick child chooses option 1 is 1, and it's 0 everywhere else. The fourth strategy is the random color strategy, and it has a 1/3 chance of choosing any observation. And that's what's coded there. And then it's a little more complicated for the majority first, for the follow first strategy, which remember copies the first, whatever color the first child demonstrates. From this, we have to use this other data input majority first, which tells us whether the majority option was demonstrated first or rather the minority option. And this equals 1. It's an indicator variable when the majority option is demonstrated first. So in that case, the follow first strategy copies the majority, and that's what we coded. Otherwise, it ends up copying the minority. But it's not because it has a majority or minority strategy. It's because it's copying whatever it saw first. Then all of this is added together. This line at the bottom here, where we loop over the strategies and we fill up the vector theta j by doing the multiplication of the probability of each strategy, the p sub s, times the probability that any particular strategy would produce the observation. This is on the log scale. So remember, on the log scale, multiplication becomes addition. And so this is why it's log ps plus log theta j. And then finally, we assign this to what's called the target instant, and this is the shape of the posterior distribution is determined by this whole vector theta j. And log sum exponent is this trick I've mentioned in a previous lecture for just defining this expression without rounding error, so it's more numerically stable. Okay, this model runs unproblematically. You should give it a try. The code is in the book, and it's in the script for this lecture as well. And here I'm just going to show you the Précis output plotted as a forest plot. These are 89% compatibility intervals, and each posterior mean as a circle. And you'll see that there's a lot of uncertainty, but certainly there's much more evidence of majority following behavior than minority following behavior or maverick behavior. Lots of uncertainty about how much random color choice there is, and lots of evidence that there of children copying whatever was demonstrated first as well. But a lot of uncertainty here. Let's say that the evidence is that children are diverse in their strategies, but there's a lot of evidence for majority preference and for following the first. It's hard to represent the uncertainty in models like this because these strategies 1 to 5 form a simplex, and so if any one of them is more plausible, then the others are less plausible. So let me try to represent this a little bit for you with an animation. Here I'm drawing from the posterior distribution, posterior simplexes for the different strategies, and just transitioning among them. And then I hope you can see the big fluctuations in the color strategy. The random color strategy are consistent with its wide compatibility interval, whereas the end strategies, that is majority and follow the first, tend to stay higher than the others. Okay, what have we learned here? My intention here was just to give you the simplest example I know of a state-based model. And state-based models are defined by what we want to know is some latent unobservable state, like a child's strategy. And what we have are what are often called emissions from those strategies. That is some behavior or sign that is produced probabilistically from the underlying state. There's typically lots of uncertainty in these sorts of analyses because of the fact that different unknown states can produce the same emissions. That is, different strategies in this example can make the same choices. But there's simply no choice but to admit this uncertainty exists and to analyze it honestly and code it up transparently and present the results. There are many, many useful state-based models in the sciences. And just as a couple of examples, the study of movement is essentially a study of using state-based models where the actual position of the person or vehicle or entity is not exactly known, but we get emissions, whether they're radar pings or GPS points, or just following the tracks of something. We can make inferences about its movement, and in particular about its movement strategy. What is it trying to do on the landscape? Learning, the whole literature on the study of learning is an application of state-based models, the internal state of the animal, what it actually prefers to do, if it's exploring or if it's in exploitation mode. All of that is part of the literature on learning, and those models have a lot of characteristics in common with the example I just gave. Population dynamics models are also a case of this. We get measurements with error of the state of the population, and the population is constantly changing. The state of the population is what we want to know, but we can't see it because it's impossible to study the whole population. International relations is an example where we're interested in the strategies that different actors are pursuing, but of course we only get the imperfect reflections of their strategies and their behavior. An example I've come across that I quite like is family planning. That is, if you observe an individual set of families who have chosen different times to start their families and different numbers of children, you may ask, well, what is their strategy? What are they trying to do, if they have any conscious strategy at all? And that's a very interesting and very important area of demography. Let's take another break. I think that's a pretty complicated bit of material there. So take a look back through it and review it, because after the break, I'm going to pick up with another state-based model, which is much more complicated than the previous one. Welcome back. For the final example in this lecture, I want to talk about population dynamics and give you an example of studying a time-varying process, something we haven't done a lot in this course, and how the study of time-varying processes of population dynamics is greatly aided by leaving the generalized linear modeling perspective behind and thinking from first principles about how the system operates. So, to review a bit, before the break, I introduced the idea of state-based models in which there are latent states, and yet we see some pale reflection of those states in the data, and different states can produce the same outcomes, and so we need a very specific type of model in which we model all the states and their behaviors simultaneously. Now, latent states can be time-varying. The entities in the population of interest can change over time. And in some cases, for example, the study of population dynamics, the states of interest are the numbers of different kinds of things in the population. And those change over time, and that's often of primary interest. As an example, I'm going to use ecological dynamics, where the states of the population are the numbers of different species over time. And I'm going to use the simplest sort of teaching example that I know. Try to make this as approachable as possible. What we're interested in here, the estimand, is how different species interact, which ones eat other ones, for example, and how do those interactions influence the population dynamics. So the classic example in this literature, it's really just a teaching example at this point, is the lynx hair data, the Canada lynx and Canada hare data. So this is a historical data set of numbers of pelts from trappers of lynx and hares, and plotted as a time series from the year 1900 to 1920, with the hares in black and the lynx in red. And you can see it sure looks like the lynx are shadowing the hares in some sense. And the question would be, what sort of ecological process would produce a population dynamic of this kind? And could we possibly learn about the dependencies between these species from a time series of this sort? This example is developed in much more detail starting on page 541 in the book. I'm going to move through it a bit too quickly, I'm afraid, here in this lecture, but I'm going to try to give you the conceptual bits that really matter. Okay, so instead of doing some generalized linear madness, let's think biologically. So it's a fundamental truth about ecological processes. I tend to think of this as the first law of ecology, that the change in any species density, its population size, over time is governed by the difference between its birth rate and its death rate. And that's a fact. That's just how populations work. This is an unassailable assumption. There's also migration, of course. Yes, we're going to leave migration out of this. But the difference between the birth rate and the death rate determines how quickly a population grows or shrinks. And so these two equations on the screen are known as differential equations, as they specify rates of change. And so the dH dt in the upper left there merely means the rate of change in hares, h, per unit time t. And in particular, it's instantaneous, but that's not the important thing to understand about this equation. It's that it says that the change at any point in time t is the difference between the number of hares times their birth rate, because birth is a per hare process. If there aren't any living hares, then they can't give birth, minus the number of hares times their death rate. If there are no hares, then they cannot die. And so both of these processes in ecology are proportional to the population size. The same is, of course, true for lynxes, but the birth rates and death rates will be different. So let's parameterize this, make it into a simple model, the world's simplest ecology model. So the birth rate of hares is just going to be some parameter, b sub h. What you have to imagine here is that there's some resource hares depend upon, some vegetable resource, for example, that doesn't vary through time in some important way. That's not a very reasonable assumption, of course, but we always start simple in scientific models, and then we learn from the ways that the model fails. And then for the death rate of hares, we're going to make that depend upon the number of lynxes. And so now I've taken capital L sub t, which is the number of lynxes at time t, and I've put it in as a component of the death rate of hares, so that the death rate of hares is the number of lynxes at time t times some coefficient m sub h, which determines how lethal lynxes are to hares, how many hares each lynx eats. Analogously for the lynxes at the bottom, I'm going to take their birth rate and make it depend upon hares. The more hares a lynx eats, the more baby lynxes it can have. How do we make this into a statistical model? Well, to do that, there are two problems we need to solve. The first is the observation model. We don't observe hares and lynxes in these data, we observe their pelts. And so at the top of this slide, in the left column here, I've got hares, and in the right column, we've got lynxes, when the models are symmetrical. We have little h sub t and little l sub t, and these are the observed numbers of pelts at each time point in the time series. And I've assigned these a log normal distribution because they're positively constrained, and their variance is going to be proportional to their mean. And the means here are defined as being the true state of the population, capital HT or capital LT, respectively, times some observation process, P. And you can think of P as the probability any particular animal is trapped. It's like a trapping rate. The other problem we need to solve is how to take these differential equations, which we use to define the population dynamics, and translate them into predictions for things that happen at each point in time, t. And it may not be immediately obvious how to do this if you haven't worked with differential equations. That's okay. They're really weird things. If you have an equation that specifies a rate of change, a differential equation, then in order to make a prediction out of it, you essentially need to add up all the little rates of change at each point in time to know what happens over time cumulatively to the population. And so the way to do that in mathematics is to use an integral. And the integral accumulates all the little changes from the rate of change at each time t and stacks them together so that we can get a prediction for a particular time point. And that's what the equations at the bottom of this slide are doing. The number of hares according to the model at any particular time, capital T, will be equal to the initial state of the population, which is h sub 1. That's however many hares there were when observation begins, plus all of the cumulated changes, which is this integral of the differential equation from time 1 to time capital T, and then symmetrically for the hares. If this is still a little confusing, in the book, I give you a little bit of R script to actually approximate this integral by just adding up little increments calculated from the differential equation, and that might help you understand it a little better. Okay, regardless, we can run simulations from this, and I give you the code for this in the book and also in the script for the lecture to reproduce the animation on this slide. What I'm doing here is I'm drawing rates, birth rates and death rates and interaction parameters from a prior distribution to show you all the possible kinds of population dynamics that are possible for some specific observation window for lynxes and hares, and to show that You can reproduce this kind of lynxes shadowing hares dynamic, but lots of other things are possible as well, depending upon the parameters. Our goal, of course, is to estimate these parameters from the data. For the data we do have, what are the most plausible values of the birth and death rate parameters for each species? And what does that tell us about the dependencies of lynxes on foxes and how much that contributes to the cycles? Again, this is going to be a stand model, and this is the most complicated model in the course for sure. I think it's worth spending a tiny bit of time just talking about the bits, not in detail, but just in terms of their function. And if you're interested in this, there are a lot of resources on modeling ODEs in Stan and in other languages like Turing that you can go and look at. I just want to give you a conceptual overview of how these models tend to work. The first thing is, and here in the Stan code, we have a functions block at the top. This is in Stan where you declare things, declare code you want to call over and over again. So in this case, we're writing the differential equations here, and that's what dpop dt is. This gives us the rates of change for any for lynxes and hares of the population at any particular time t. And you can see down here the differential equations right here. And we're going to use this function to compute the cumulative change to time t just a little bit further down. But you see the code here and how it reflects the differential equations on the right. Further down in the transform parameters block, we call that function over and over again. Remember, that function is called dpop underscore dt. And this integrate ODE arcate45 function does all the little incremental math that's needed to compute the cumulative change up to any particular time point. And so what the code is doing here is it takes every time point in the data for which we have some observations, and it gets predictions using specific sets of parameters, Markov chain samples, up to that particular point. Then finally, down in the model block, we have the observation model. And this is where the observation error comes in, because pelts are not actually whole animals, and we observe many fewer pelts than there are animals. And so that we have this process in the model as well. Okay. I encourage you to take a stab at running that model using the full code that's in the book or in the script that accompanies this lecture. And what I'm showing you here are samples from the posterior distribution, or transitioning among them, for what the model has learned. And the red and black points are the actual observed data in this case. You'll see that there's actually still a lot of posterior uncertainty about the actual state of the population, which is what the curves are. And that's because there's a lot of process error here as well, just because of the fact that the data are pelts and not animals. But even if the data really were animals, we never really observed the whole population in any particular study. And so this kind of uncertainty is typical. But that doesn't mean this isn't useful, because we can still learn about the causal forces inside these models when there's substantial uncertainty about the process. And in addition, we can learn from the ways that the model seems to be failing against the actual data as well, because it's a scientific model and the parameters have scientific meanings. There are other kinds of data we could bring in to aid us in determining their values or setting informative priors. Okay, I want to sum this up. This is a complicated example, and I've gone through it way too fast. I know, I'm sorry. But the goal is not to teach you all the details of the coding, which are of course important if you're really going to do a project like this or any other kind of population dynamic modeling project. Instead, it's to give you an impression of the possibilities out there, and so that when you start your next scientific project, you don't start by thinking of a generalized linear model, but instead by thinking about the theory that's required to get you to a successful data analysis. Real ecologies are, of course, much more complex than the example I've shown here. They have more than 2 species in them. There are other animals that prey on hare, and lynx may not actually prefer to prey on hare at all. But regardless, if you don't have some kind of causal model that you start with, there's typically little hope of understanding any interventions you'd like to do in these systems. That is, if you just want to fit curves and describe the data that you've collected, fine, just use generalized linear models. But if you want to do more than that, if you want to do science, then it'd be good to start somewhere else. The good news, of course, is that as simple as this kind of framework is, it's extremely successful in fisheries management. Many of the fisheries in the world are managed very effectively and sustainably, and they're done so with population dynamic models that are quite similar to the ones I've shown you here. Okay, this has been a long lecture, and we started with a lot of disappointment thinking about generalized linear models. And what I've tried to do is show you not that generalized linear models are bad, because there are square pegs that go in square holes, and that's what we should do with them. And sometimes just when getting a project started, it's fine to use generalized linear models as well. But eventually, in mature sciences, we move beyond that, and we have bespoke causal models scientifically tailored to particular problems. We put our round pegs in our round holes, and this brings elation. Every field has its own problems with measurement and its own sorts of complicated time dynamic phenomena that it's studying, and so every field is going to need its own statistics. But if every field is just using t-tests and linear regressions, then they will never be able to live up to their scientific potential. Of course, it's true as well that it takes a long time for every science to develop those candidate tools. And so if any particular science is having statistical frustrations, that doesn't mean it's hopeless. And if you are ever having particular statistical frustrations, that doesn't mean you have no hope. So the core message I want to get across here is that we should stop doing statistics. Can I say that? Yeah, I'm going to say that. We should stop doing statistics, or rather, we should postpone doing statistics until we've got the science straight. We should put the science before the statistics and make the statistics serve the science. And the reasons, well, I've been laying them out now for weeks in this course. Epicycles are fine things to use consciously with awareness, because there are things we don't understand yet about our systems and we need to approximate them, but they're only going to get you so far. And at some point in research, we have to replace those epicycles with real scientific models by putting aside any thoughts of statistics and just thinking about the causal systems and trying to analyze them. Now, scientific models are also flawed, but the flaws are productive. We learn from the ways that they underpredict or overpredict, the ways that they miss. Ultimately, there's no effective empiricism without theory. I'm sure I'm not the first person to say that, but I've tried to persuade you of it in some of these examples as well. So this elephant on the right, what is it doing and why is it here, has probably been distracting you while I talk. This is one of my metaphors for what it's like to learn to do, well, science. So when elephants are born, they don't really have very good control of their trunks. And now their trunks are incredibly agile and useful tools that they will use throughout their very long lives to do amazing things. They have tremendous trunk dexterity, as it were. But young elephants are like the one on the right. Their trunks kind of flail about and they don't have a lot of control. And that's often what it feels like when we start to learn scientific data analysis. There's a bunch of tools. They're like rocket ships, and at the press of a button, we can launch them. But we don't really know how to fly them yet, or even how to, certainly not how to design them. But you have to be patient with yourself, just like this little elephant has to be patient. And mastery comes with use, and it takes time. But mastery comes with safe use. That is, we need to practice and learn and test what we're doing so that we can build cumulative research. And of course, experts, people who make this stuff look easy, it only looks easy because they've learned a bunch of productive habits that make the work safe and productive, help them find their mistakes as they make them, because all experts continue to make mistakes, and then correct them and document them so that the next time they will make a different mistake instead. Okay, that is lecture 19. We're in week 10. We're coming into the end here. In the next lecture, I want to talk about the larger sociological context of all of this material. And so I hope you'll join me.